Hello, everybody. Thanks for joining. We will give it 30 seconds and then we'll get started. Okay. Thank you, everybody, for joining the webinar. I'll run through a few housekeeping points and then hand over everything to our webinar chair and the co-chair of the Croplands Research Group, Hiro Golani. Here are a couple of housekeeping notes. The webinar is being recorded and the video will be made available for future viewings via the GRA website. And today we will be hearing one presentation that will be presented by 4 speakers, followed by a clarifying Q&A session. Throughout the presentations, please feel free to submit your questions as we go via the Q&A function, and we will get through as many questions as we can. And if there's a question that you see that you like or agree with, you can use the upvote button so we know this is a popular question. And finally, if your question is not answered, or you see it's been dismissed, this doesn't mean it won't be answered later. We will summarize all questions and make additional answers available on our website at a later date. Thanks again, everyone, for joining this webinar, and I hand over to Hiro.
Good morning, good afternoon, or good evening, wherever you are. I am Hiro Golani, US lead for Cropland Research Group and one of the co-chair for Cropland Research Group of GRA with Rosa Mosquera and Lozella Martin. Welcome. This webinar, we have a 4th speaker. I am going to introduce our 4th speaker first, and then we will start the presentation. Dr. Roberto Valdivi is assistant professor and senior researcher in the Department of Applied Economics at Oregon State University. He is the co-leader of the regional economic team of the AgMIP and co-developer of the trade-off analysis model for multi-dimensional impact assessment. His agricultural economic work started with the project funded by the International Development Research Center, Canada, in Peru and Bolivia. He worked for the International Potato Center and later for the trade-off in sustainable agriculture project funded by the US Agency for International Development. His main international research focused on Africa, Asia, and Latin America, as well as the US, and he has been consultant to several agricultural research and development institutions such as FAO and Bill and Melinda Gates Foundation. the International Fund for Agriculture Development, and several others. He has extensive experience on analysis of agriculture production system and impact assessment, trade-off analysis, foresight, assessing economic, environmental, and social impact of policy and technology, climate change impact, adaptation, and mitigation, including analysis of economic and of terrestrial and geological carbon sequestration. Valdi received a PhD in development economic and environmental economic from Wageningen University in Netherlands. Dr. Tao Li, a senior scientist at the International Rice Institute. He leads research studies on environmental and crop modeling and coordinates modeling activities institute-wide. He leads the rice team of the AgMIP between 2010 and 2017. As a member of AgMIP, he continuously participates in research activity in AgMIP and rice teams. He is leading international research project and modeling research activity in several international research projects. His current research focuses on greenhouse gas mitigation and improvement of rice production by combining field experiment with modeling technology, and leads the initiative of Global Rice Crop and Greenhouse Gas Benchmark Database. Dr. Snelly Shukola McDermott is a climate scientist and modeler, associate professor and chair of the Environmental Study Department at New York University. Her research sits at the intersection of climate change and variability, land system and agriculture, with an emphasis on land atmospheric interaction and climate change's impact on crop and food security. She is also a research affiliate at the NASA, where she helps to develop and use NASA Model E Earth System Model, and has served as climate co-lead for the AgMIP, which conduct integrated assessment of climate change and food security around the world. She is a Fulbright Fellowship awardee and Andrew Carnegie Scholar, which supports her work in investigating avenues of climate-smart rice production in South and South Asia. She holds a BA in physics from New York University and master and doctorate degree from the Department of Earth and Environmental Science at Columbia University, specializing in atmospheric and climate science. Prior to her appointment at the New York University, she was NASA postdoctoral fellow at NASA GISS in New York City. Eric Menendez is a senior research associate at Columbia University Climate School and the NASA Goddard Institute for Space Study, where he serves as program manager for AgMIP. He supports AgMIP coordination units by working collaboratively with scientists and researchers. Columbia University officers and sponsor agency officials on the overall research coordination and financial management of the program. He was chapter scientist and contributing author for the food security chapter in the IPCC special report on climate change and land. He also leads the organization and execution of multidisciplinary workshop worldwide. Eric has a master in climate and society from Columbia University and baccalaureate in chemical engineering from, I think I will, technological Monteria or ITESM in Mexico. I am looking forward to their presentation. Thank you all for being here. Take it away, Roberto. The floor is yours.
Thank you, Hero. Yeah, thank you for those introductions. I think the way that we are going to do is Eric will start with the introduction of AgMIP and the MACV project. And then we'll follow up with the climate modeling with Sonali and the crop modeling with Tao, and we'll finish with the economics with me. So Eric, let's go ahead.
Yeah, thank you, Roberto, and thank you, Hero, for those introductions. So yeah, as Roberto said, I will start off with I will try to keep it brief introduction of AgMIP. So let me just share my screen. And of course, now this is here. 1 second. There we go. So the topic for today is co-benefits and trade-offs of agricultural mitigation and adaptation in rice-based cropping systems. This is work that is being led by AgMIP, the Agricultural Model Intercomparison and Improvement Project. AgMIP is a partner of the GRA as of 3 years ago, 2019, I think is when we joined. Really, we are have been interacting more with the integrative research group of the GRA, but so we really appreciate this opportunity to really get to present some of our work to the Croplands group and maybe find ways to work closer together. We want to appreciate support from ACR really through the AgMIP becoming a partner of the GRA. We were contacted by ACR in Australia to do this work in rice-based systems, particularly in Bangladesh, which we'll go into the details, in the presentations. As you can see from the bottom of the screen, we work together with several colleagues in Bangladesh, including the Bangladesh Agricultural Research Institute, the Bangladesh Rice Research Institute. We worked with CIMMYT's office in Bangladesh. And then, as you heard, some of us who are on the call today, I'm here from Columbia, Roberto from Oregon State, Sonali from NYU, and Tao from Erie, just to show, that this was very much a collaborative project. But like Roberto said, so I just give a very quick overview of AgMIP. In particular, so the mission of AgMIP really is to provide science-based agricultural decision-making models and assessments of climate change to achieve local to global food security. So we work, at all scales, from the subnational all the way to global. Let me just go to here. AgMIP really at its core is a network. We're a community of researchers and particularly modelers looking at agriculture, climate, and really all aspects of the food system. Currently, we have about 1,200 people really all over the world who contribute. Basically, anybody who's doing modeling or working in the field who's interested in being part of AgMIP, we are very open. As I've been saying, we convene scientists and stakeholders. It's not just a research side, or it's really working with stakeholders always from the beginning to conduct multi-model assessments. That's one of the key parts of AgMIP, that we don't subscribe to any one model. Anybody who has a model who wants to as I said, the name is intercomparison and improvement. So it's comparing the different models and through that process really, improving them. We go all the way from biophysical out to economics. We have climate modelers, we have crop, livestock, all the way to the economic part. And anyway, yeah, we have the economics right from the beginning. That's something that we always want to highlight. Sometimes the economic just kind of comes at the end. But it's also something that we have always included from the start. And again, really the outcome that we're trying to achieve is providing the science base for decision making, for example, countries working on their NDCs, their nationally determined contributions, or their NAP, their adaptation plans. We want to provide that science base for them to make those decisions. To prove that we are this worldwide science community, and AgMIP has been working since 2010. These are just some photos from the workshops that we hold. So this is a really big part of what we like to do with AgMIP, is bringing together the community. We have what we call our global workshops, where it's basically anybody from all the different parts of AgMIP that I mentioned coming together. But we also do specific, regional workshops. Like here you can see this from Sub-Saharan Africa, South Asia, Latin America, and then some specific examples for particular activities. Like we had like a wheat, all the wheat modelers coming together, all the rice modelers, all the corn, maize modelers. Just last year, we held our 9th global workshop, was held right here at Columbia in New York. And we're already in the process of planning our next one. So please, if you are available and would like to travel to Mexico in 2025, we're going to hold our AgMIP 10 in March 31st to April 4th, 2025 at Summit. So I won't go through this whole thing, but I just wanted to show it. So again, AgMIP really works in many, many different aspects. We have climate scientists, agronomists, economists, IT experts. Just some of the examples here you can see with, we do work on pests and diseases. We do work on ozone. We're now bringing in aspects like, artificial intelligence and machine learning. So again, if there's activities that you are interested in, we have co-leaders for each of these activities, and anybody can be part of it. Or if there's a new area that is not covered by AgMIP but would be relevant, we are always open to people, who are interested in leading a new activity, becoming part of AgMIP. Today, really, we will focus a little bit more on this sort of like the regional integrated assessment side of AgMIP. And I just want to say, agmip.org, if you want to learn about any of these things, you can visit our website, because I obviously don't have time today to go into all of it. But yeah, so today, really, I wanted just to highlight a little bit the what we call our regional integrated assessment approach, which is a methodology that AgMIP has been using really from the beginning. As I've been describing, obviously a key part of it is, defining the climate risks, utilizing, as I said, multi-models. We have here representing, the climate, the crops, the livestock, the economics. But really, right from the start is with stakeholders, right? Engaging stakeholders, having a network of experts. In this particular project in Bangladesh, as I said, BARI and BIRI, the Agricultural Research Institute, the Rice Research Institute, were part of it right from the beginning. But we also interacted with some of the ministries in the country. Really, in an ideal world, when we do this sort of AgMIP projects, we travel to the region. We're there. We're holding multiple workshops. Two things happen with this. This is the Bangladesh project was very much a pilot, and we are hoping that it will be, we will have an opportunity to have a few more phases to this. But what you will hear today was a pilot project, and it also took place mostly over COVID. It really started over in 2021. So we were able to hold one workshop in the region, which Roberto went to, and maybe he'll say a couple of words on that. But even using technology, and we did some webinars, some Zoom webinars, to get that feedback from people in the region. But anyways, I don't want to take too much longer, but basically, as I said, the idea of this graphic is really kind of showing this, these arrows going back. Like we're always, we put forward something, we're engaging with the stakeholders. We have this process where we co-design with, everything is called, right? Co-design pathways, co-design adaptations, working with the policymakers and decision makers and stakeholders. These pathways, we're able to, using the models, in particular Roberto's model in the economics, like developing what could a potential future look like, and then testing using the models, what would the results be. We can look even at, how many of the farmers would actually adapt, would actually adopt the adaptation that we are proposing, all the way to assessing, vulnerability and economics, poverty rates, net farm income and all that. And, Roberto will talk a lot more about that in his presentation. But the key thing is this, this going back is a very iterative process of working with the stakeholders. Just a couple more slides. So, and what we're showing, AgMIP for a long time really was much more focused on the adaptation and sort of resilience side of things. Through our partnership with the GRA, we really have been able to kind of bring in the mitigation side. There had already been some work on this, and Vietnam and India. Roberto and Sonali had already been leading some of the work on this mitigation and adaptation piece. But yeah, now that we're working closely with their GRA, we really are bringing the mitigation much more strongly. And in particularly for the Bangladesh project, it was thanks to our partnership with GRA. And we are referring to mitigation and adaptation co-benefits. So we're, for a shorthand, calling it the MACB project. Just very quickly, with this, we were trying to trial a modeling approach for quickly and efficiently determining the likely best options, right? So we're using the models, see what practices could deliver both mitigation and adaptation benefits or trade-offs. Of course, the ideal is the co-benefits, but we also have to consider that there might be trade-offs between the two. And the long-term outcome, as I said, we're hoping that maybe there'll be some future phases of this is to accelerate the process of identifying the most promising options and then progress to trialing and scaling more quickly than has been done in the past, knowing which are the options that are actually better, and then those are the ones, that can move to trialing and scaling. And then this is just a very simplified way of what we did in this project. And again, Sonali, Tao, and Roberto will really go into the details of this. But with the climate, we looked at current climate, but then also going into the future and future climate change, looking at two examples: a less extreme, not as much warming, not as much variability in precipitation, and then a more extreme climate change where if temperatures become much warmer or there's much more variability in precipitation. And then using that information into the crop model with the NDC ORISA, which Roberto Tao will go into. And as I said, in AgMIP, we're really, ideally, we like to use multiple models and compare them. Because this was a pilot project and fairly short, we really just used the NDC ORISA here. And then into the economic model, which is, again, what Roberto will be showing. We looked at comparing conventional farming management, and then the system of rice intensification, as known as SRI, and then also using continuous flooding as an irrigation practice, which is the more commonly used, and then also what happens if you move towards using alternate wetting and drying, or AWD. All of this in as I said, in the current climate or in different potential future climates. Again, all of it coming together to, okay, what are the, as far as emissions or mitigation, and then as far as resilience, so like yields of the crop, rice in particular, or rice in this case, and water use. Which places do you see the co-benefits? Which places do you see the trade-offs? So anyways, I'll stop there and I'll pass it on to Sonali to talk about the climate piece.
Great, thank you, Eric. I will share my screen now. All right, are you all able to see that?
Yes.
Okay, great, wonderful. So I'll present a very quick overview of our climate team activities as part of the AgMIP MACB protocols that Eric has just introduced. And I conducted this work in conjunction with a whole range of colleagues, in particular, Mohammed Basler Rashid, who's a meteorologist at the Bangladesh Meteorological Department. So our climate team's main objectives in AgMIP are to provide scenarios of future climate change for our regional integrated assessments, downscaled for particular sites. And in this case, particularly for our MACB sites, to get a sense of the uncertainty across future climate change that's related to human decision-making. So for example, following a high ambition mitigation pathway, such as SSP 1.9, SSP standing for shared socioeconomic pathways, or different narratives or storylines of change, ranging maybe even all the way up to our worst case scenario, our SSP 8.5. And so what this maps for us and what's used by the Intergovernmental Panel on Climate Change is a range of uncertainty in decision-making and our ambition to tackle climate change that we can translate to a site-based local level to understand what the implications of a worst case or very high climate change scenario would be from a high mitigation scenario. And so we are leveraging the latest climate model assessment, the IPCC AR6, with the latest version of the climate models, around 40 that have contributed to AR6. And what's interesting about this too is that we can start to think about not just the impacts of climate change on agriculture or on crops or on food security, but also the contributions of agricultural management and land use to the climate system. What we're trying to get at with MAC-B that's distinct from what we've done previously in AgMIP is to move beyond adaptation to also thinking about avenues for mitigation and how this potentially feeds back and changes the overall climate forcing. And so what you're looking at here is a still zoomed out, but starting to get more regional view of climate change in the AR6 assessment. And so what you're looking at here are different levels of warming from 1.5 to 2 degrees C all the way through 4 degrees C for the Asian domain. And here we're looking at mean temperature, changes in precipitation seasonally, December through January, February, June, July, August. And then on the right-hand side here, you're looking at the change in the maximum temperature over 35 degrees C, which would have impacts on both human systems, croplands, and natural systems as well, too. And overall, for this region, we see a few key trends emerge. Firstly, looking at just the rainfall, we see some increases, fairly significant in rainfall over different seasons and at different levels of warming. And in general, we note that our climate models show that both the annual and summer monsoon precipitation will increase over the 21st century. And it's likely, although there's more study that needs to be done still, that the variability in this rainfall will also increase, potentially leaning towards more extreme conditions. Alongside temperature increases, we also note that heat waves and humid heat stress that accompany higher atmospheric moisture may also be intensified over the 21st century. And again, this will have impacts on crops and also other aspects of farming systems like labor. And so we're really trying to understand how these kinds of changes actually scale to the local level and what that means for combined mitigation and adaptation in farming systems and cropping systems, and in our case, particularly rice. And so what you're looking at here are the changes in precipitation on the y-axis and temperature on the x-axis for the population, the current population of climate models. In this case, we've taken a subset of about 24 climate models. But one important thing to note is that it's rather prohibitive still to run 24 plus climate models through a crop model and then an agricultural model. It just increases the volume of simulations and scenarios to a point where it becomes fairly intractable. And so we need a way to subset across the model space, which is what you're looking at here, across the precipitation uncertainty and across the temperature uncertainty, such that we can provide stakeholders and decision makers with a range of climate outcomes, but also approach our simulation and our experimentation in a more tractable way. So it's prohibitive to run every climate model. But the other important thing we've revealed in AgMIP over the last decade is that it's inaccurate to run just one model too. And that's historically been what's been practiced, is that you select a model for a particular site, maybe one climate model, which is one among many of these dots, and you run with just that one model. But what happens if you select a subset of models, of multiple models that explore the range of uncertainty? You might actually wind up with very different outcomes from your crop modeling and your socioeconomic modeling portions. And so that's what we're trying to address here. And so for this particular work, we've chosen as an example a subset of 2 models with the intention of future work expanding to 5 models that sample across this space. And really what you're looking at across this space is the range of change that's projected through all the individual models. Some models show wetter futures while others show driers. Some models show warmer futures, while very warm futures, while other models are still warm, but perhaps not as warm as the most severe models. And so what we've done is we've taken a sampling of just 2 models here to show you what this assessment produces. One, our HADGM model is what we're calling more extreme climate change, where we're leaning towards much warmer conditions, well over 2.5 degrees Celsius mean temperature changes over the relevant season. And one other model, MyRock 6, that still shows a warming, but not as severe. Our models also sample across a smaller range of precipitation, including drier conditions for the less extreme climate change, but not by much, and slightly mean to wetter conditions under the more extreme climate change. And so here we're really looking at temperature, mostly because we're working with rice-based systems that are experiencing some level of irrigation, whether it's full flood irrigation or ponding versus alternate wetting and drying. And so we expect that the rice crop would display more sensitivity, not just the rice itself, the yields, but also methane, for example, would display more sensitivity to the temperature changes, which is what we're sampling over, versus the precipitation changes. And so kind of zooming in a little bit more to capture a bit of our domain, one thing to note is that these models are still fairly coarse. We've used a climate downscales product at about 25 kilometers resolution, but we know that there can actually be a whole population of farms, particularly smallholders, within a 25-kilometer resolution. So overall, what you're seeing here are the more extreme climate change and the less extreme climate change for precipitation and rainfall. And while rainfall goes up, and so does temperature, we're interested in what these differences across the levels of warming and maybe across the water as well too mean for our rice and also our other variables such as water use and methane. And with that brief introduction to how we think about climate change and our multi-model approach, I'd like to turn it over to our lead crop modeler on this, Tao Li, to explain his process with our DNDC Oriza. Tao, would you like to share?
Yeah. Okay. I hope you can see.
Yes.
Yes.
Okay. So, thanks for the chance. And good morning, good afternoon, or good evenings, whatever you are. So, under umbrellas of the assessment systems of AgMIP, we did our crop modeling exercise in there. In our teams, we have the 4 people. That's me, and take from Summit and Uma, and Apple come from the Barry and Barry. So of course, we also have the great support from other team members. Without their support, we cannot do this job as so far. So I try to give the brief as much as I can. So this is a process of what we follow in our modeling, crop modeling exercise. we start with data collection and probably come from the other group or from other source. So after that, we do the data cleaning and as we organize the data into the model, we have the number of the cycles to do the calibration and validation, follow the standard protocol, and try to minimize the difference between model predictions and the observations, and also try to quantify the uncertainties of the model prediction. As long as we have the confidence on the crop predictions, we use the crop model into to do the scenario evaluations. And the scenario probably include different cropping systems or crop management in there. Now so we can generate large number of this data. We can use this data to do the analysis on co-benefit and trade-off in terms of the yield and environmental indicators, and also the source consumptions. Of course, this results will be used in the future economic modeling. And because this is, as Eric mentioned, this is pilot studies. We only use the DNTC and DNTC horizons for this exercise. So the data come from for the crop come from different sources, and rice yield and the crop management has come from the field survey conducted in Bangladesh between years 2019 to 2021. Soil data was extracted from the soil grade 2, but we use the local soil profile data to collect the bias. And the weather data come from the Sonani's group. So the modeling and calibration and validation, we managed to work on the two most popular varieties in Bangladesh. After the data quality control, we selected almost 1,500 sites from 4,400 sites for our model calibration and validation. We separate this 1,500 sites randomly into 2/3 for the model calibration and 1/3 for the model validation. During the scenario evaluations, we work on 3 climatic conditions that's already described by Sanani. And we work on the 2 cropping management systems that's called convention, which is current farming practice in there, and also SRI, some already have some farming practice this management in there. I give the little details what is SRI in there. So we work on the 2 water management schemes, continuous studies, and adaptive management. Unfortunately, we didn't work on the site-specific conditions. Because of this the pilot studies, we do it in a short time. So adaptive management over all sites is the same in 5 days wait and 7 days dry period. For the conventional scenarios, we work on the 8 administrative districts, and the SRIs only work on the 3 districts. So after several cycles of model calibration and validation, we are able to minimize the difference between the model prediction and the field survey data. We are even realize we have some uncertainty in there, but we are quite happy, so we are able to present most of the case. So generally, the uncertainty will be less than 21%. And considering the data quality of the field survey data, we are happy we are able to do that. We have the confidence on the model predictions. We didn't have the data about the greenhouse gas emission from field survey data, but we are quite confident with the DNTC models because it is already used for the quantification of greenhouse gas emission and more than hundreds study case overall rice production regions. So this is some results. So, if we associate with the application of AWD management, we see some difference between current climatic condition and the future climatic condition. Generally, we have a little bit very small decrease in yield, and so we have a huge decrease in the greenhouse gas emission. However, this kind of the reduction, or we have the huge variations in different locations over spaces, over spatial scale. So you see, so from the decrease to the increase, or decrease very much, increase also very much in some in a different location. So if we going to look at the results in the district level, so we see, so with the application of AWD, we are able to maintain the green yield, and we can reduce the total greenhouse gas significantly, and also the greenhouse gas emission intensity, and we are able to maintain this nitrogen use efficiency and reduce irrigation water a little bit. So if we look in size by size and among different different districts, you see this they have very much different. We have certain sites have the yield increase, and we also have the significant number of sites have the yield decrease. But even the decrease is very small, but still a little bit of decrease. But definitely, we have the significant decrease in the total greenhouse gas emission. And we have the water saving in the most sites, but in some districts, some because the soil condition or weather condition or combine of the soil and the weather condition, so the probably also have the even some water increase in the if we as the application of AWD. So if we say that what is climate change impact in there. If we look in the also allocate in the district levels, we see so we can, under the climate change conditions, we are able to maintain this yield, but it's not good in the greenhouse gas emissions. We are probably we have some kind of increase in the total greenhouse gas emissions, especially the significant increase in the methane emissions under climate change condition. If we use the same crop management system. And there's also say we have the increase in the greenhouse gas emission intensity, and however, we are able to improve the water use efficiency. So if we use the AWD on the future climatic conditions, we are able to maintain the yield, and so we have the big decrease in the total greenhouse gas emission, and a big decrease in the methane, and the big decrease in the greenhouse gas emission intensity, and we can improve the water use efficiencies also. And so now as the SRI applied this, so we have under the current condition, if we use the SRI technologies in there, we say that in our tests, 2 districts out of the 3, we have a significant increase in the yield, and this we also can achieve the total reduction on the total greenhouse gas emission, but we probably have some kind of increase in the N2O because the number we presented in the figure, so you need the time 2s and there. So in order we want to say that the same unit as we want to put all numbers in the one figure. So we do the scalings about the N2O and the organic fertilizer application. So with a huge amount of organic fertilizer applications, we have the little bit increase in some districts in N2O emission, but generally say we reduce the greenhouse gas emission, increase the yield, reduce the greenhouse gas emission intensity, improve the nitrogen use efficiency, improve the water use efficiency with the application of SRI under current climate condition. If we going to combine the SRI and AWG management together, we compare the future climate condition and the current climate condition, we are able to maintain the yield, but we are not able to completely trade off the positive impacts from the climate change and the greenhouse gas emission and the greenhouse gas emission intensity. And even we have some improvement in the water use efficiency and maintenance the nitrogen use efficiency. Remember, we have the large amount of the use of the organic fertilizer. So if we compare the SRIs and the SRA and AWG combines, compare to the convention and the continuous flood condition on the future climate condition, again, so we can increase the yield and loss, and we will have the under this comparisons, we have the significant decrease in the greenhouse gas emission and significant increase in water use efficiency and nitrogen use efficiency. So what's the message you can bring to the home? The first one, for the scaling up of any technology, we needed to do it in the site specific. So our modeling technology probably we can help with that to optimize the management in the site specific condition. And second, so the climate change will increase the greenhouse gas emission, and AWG management is a good practice to maintain the green yields and reduce the greenhouse gas emission. SRI also is a great approach. We can improve the productivities, to have the good food security, but we have to carefully work on the greenhouse gas aspects. We needed to control the greenhouse gas emission. At the same time, we need to pay attention. This SRI practice probably is not easy to scaling up because the limitation of the source of organic fertilizer. We remember we use organic fertilizer a lot for this SRI management. And in terms of this, I finished my brief summary and move to leave it to the Robert for the economic modeling.
Thank you, Tao. Can you finish sharing so I can start sharing? Okay. Let me. Let me see. Can you see my screen now? It's on the right.
Yes.
Okay. Okay. So this part, it's about integrating what you have seen already, climate, crops, and economics, with the goal of assessing the mitigation, adaptation, co-benefits, and trade-offs of rice farming systems. So the goal of what we call the economic modeling is to really see how we can evaluate the impacts of climate change on rice-based production systems, and more specifically looking at estimating the gains and losses due to climate change. Not everybody loses and not everybody may gain because of climate change, and estimate the proportion of households that are vulnerable to climate change, meaning which farmers or the proportion of farmers that may lose income because of climate change. And then associated to those gains and losses, what are the impacts on socioeconomic and environmental outcomes, like farm income, or the total emissions in the region. The second alternative is, so once we look at the sensitivity of climate change onto these production systems, then the question is evaluating the potential trade-offs and co-benefits of changing rice management systems, right? In this case, what Tao mentioned, going from conventional continuous flood rice systems to using conventional with alternate wetting and drying, or to the system of rise intensification. So this approach allows us to estimate the potential adoption rates from switching from those management systems and assess the economic benefits associated to those adoptions, and then evaluate the trade-offs and co-benefits between those socioeconomic and environmental outcomes, like farm net returns and emissions. To do this, we use the trade-off analysis for multidimensional impact assessment, or TOA-MD. The TOA-MD model is a model used for impact assessment and uses a statistical description of a heterogeneous farm population to be able to simulate the adoption and impacts of, for example, a new technology. For example, if we are introducing a new crop variety or changing the crop management, so the model can evaluate what would be the potential adoption rates of switching from the current system to this new or alternative system. Then we can also model the change in environmental conditions, like, for example, climate change, right? And we can also look at policy interventions like payments for ecosystem services, carbon sequestration, subsidies, and all of that. But one key element is to mention is that the model is not a farm level model. Okay, the idea is to be able to represent the distribution of outcomes on a population of farms. And why is that? We start with characterizing, you see the figure on the right, we start by characterizing the activities on a farm, right? So farmers may have maize and rice and livestock and other activities, plus the household activities. But when we look at that population in a region, we know that farmers manage their crops differently. They may have different crops. They may have different biophysical conditions like soils or maybe even weather conditions, right? Because they are on the other side of the hill, or so this produces basically systems that are being used in heterogeneous populations, and that characteristic is what allows us to estimate who gains or loses, for example, from climate change, as we'll see in a little bit. So the way the model works is we think about simulating experiments where we have the base production system, or the current production system that we call it System 1, and the alternative system, System 2. And we look at those at the different outcomes. For example, let's think about farm returns. So if we may have an example where the current system produces E1 in this figure, as expected returns or expected income. And then we propose, or somebody comes and proposes a new system or a management system or a new crop variety that produces an expected return of E2. So the traditional analysis that uses representative farm approach or aggregate values that compares means, right? So we will look at this and say, oh, the System 2 produces higher net returns or higher income compared to System 1, so that's good. The problem with that is that approach, or those approaches, cannot model that adoption rate or the distribution of impacts associated to those adoptions. And again, why is that? Is, as I said before, we have a distribution of farms, right? And not everybody have the same conditions, not everybody manage their systems in the same way. So what we really have is not just the mean values, but we have a distribution of outcomes for System 1 and System 2, right? So the model, this model, what it does is to represent this population of farms using the distribution of outcomes, for example, expected returns. Then using this model, we are able to estimate the adoption rate as the proportion of farms that would switch from System 1 to System 2. And what are the consequences of that adoption, right? Because if you think about that, when we have the System 1, so we have a one population of farm, let's say, using that new data-based technology. But once we want to introduce a System 2, there would be now two different populations, the ones that adopt the System 2 and those the remaining System 1, so the adopters and non-adopters. And those will produce different levels of outcomes, like different levels of income. And if we're talking about emissions, different levels of emissions. Right. So that's why it's important to capture the socioeconomic, biophysical, and environmental heterogeneity to do this analysis. And I talked about this example in terms of adoption of a technology, but talking about climate change, it's a similar approach. The only difference is that when we talk about technology adoption, farmers have the choice, right? They can self-select into staying in system 1 or move into system 2. With climate change, they cannot choose, right? They cannot choose, I stay with no climate change or go to climate change. So everybody's affected by climate change. But when we are able to characterize the production systems in a region, in the case of climate change, what we can estimate is who loses and who gains from climate change. Okay, so that's the approach that we use using the trade-off analysis model. Just quick, I'm not going to go in detail on this figure, but the sequence and the data needed to do this is we use the outputs from the crop modeling, which uses the climate and the crop management data, right? So we use simulated crop yields for all the system scenarios, and also the greenhouse gases emissions. For this analysis, we use these 4 indicators: methane, N2O, water use efficiency, and CO2 equivalent. Then we also use plot and farm level economic data, right, for all the rice production or systems that we are looking at. So crop management, input use, cost of production, prices for inputs and outputs, and the land allocation. And we also use information in terms of household size, farm size, off-farm and non-farm income. And then with that information and the model, then we're able to estimate the impacts of climate change, adaptation, and mitigation based on those distributions I mentioned before for system 1 and system 2. So how do we set up our what we call simulation experiments? First, we have these 3 rice management systems, right? First, the conventional continuous flood. Okay. Then we have the conventional with alternate wetting and drying, with AWD. And then we have the system of rice intensification with AWD. So those are our 3 management systems. Then we have our climate. We have the current climate, and then we have the climate change, as Sonali mentioned. So we have this less extreme climate change and the more extreme climate change. Okay. Then we have our strata or the population of farms. In this case, we're focusing on 3 regions in Bangladesh, and these names are abbreviated. The full name is Gopalnang, Kichonderang, and Lalminorat. But within those 3 regions, we stratify further by 2 types of farms. Small rice producers that have less than 0.5 hectares, and large rice producers that have more than 0.5 hectares of rice on their farms. Okay, so it's in total 6 strata. So here's the sets of scenarios that we run. So the first part, as I said, is looking at what are the impacts of climate change on these rice systems. So you have this column, system 1 and system 2. And system 1 is the management systems under the current climate, and the system 2 is with the climate change, right? With the less extreme and the more extreme climate change. So, for example, the experiments 1 and 2 correspond to the conventional rice system with continuous flooding, right? Under current climate compared to the 2 climate change scenarios. The experiments 3 and 4 are for the conventional with AWD, right, under current climate and then under future climate. And the 5 and 6 is the SRI, right, under current climate and then with climate change. So this is intended to see to evaluate what is the sensitivity of these management systems to climate change. Now, the next step is, okay, let's look at switching of management, and our base management is the conventional continuous flood. Okay, and the idea is to look at what are the potential adoption of, in this case, moving from conventional continuous flood to AWD, and from conventional continuous flood to SRI. And 7 and 8, the simulation experiments 7 and 8 are under current climate. Okay. Now we replicate these cases under climate change. So we have, again, moving from conventional continuous flood under the less extreme climate to AWD and SRI under that future climate. And the same thing for the more extreme climate change. So we have in total these 12 simulation experiments that combines the impacts of climate change and then the adoption analysis going from conventional continuous flood to either conventional AWD or SRI under current and future climate. So let's look at some results. But before that, I'm not going to go in detail in this, but this is this is showing is the contribution of the crops that are grown on the farms to total farm net returns. So the first column is for farmers using the conventional continuous flood. The second one is for farmers using the continuous AWD, and the third one is for SRI. And these are the different regions and strata. It's difficult to see the numbers probably in the screen, but the orange sections of the pie is the rice. And so the contribution on the continuous flood from rice to net returns is between 30% to 100%. So there are two regions where farmers only grow rice. With AWD is between 30 to 51%, and with SRI is between 30 and 52%. And the reason I'm just showing this is because just to make the point that we are not modeling, or we are not just including rice in the analysis. We need to include what happens to the other crops, right? In this case, they have the light blue part of the pie is aggregated wheat, maize, and pulses. And then farmers report a lot of other crops that they grow on their farms. That's the dark blue case. Now, for this analysis, because we wanted to look at the sensitivity of climate change and adoption of rice, we kept constant these other crops. We didn't do any change or modeling or model the other crops. So we only modeling rice as part of the system. Okay. All right. So let's look at the results in terms of the impacts of climate change. The two columns show the two climate scenarios, the low or the less extreme, and then the right-hand side is the more extreme climate. The first row is the proportion of households that are vulnerable to climate change. Okay, and then you see the orange ones is the conventional continuous flood. The blue is the conventional with AWD, and the green one is the SRI. So the first thing that we can notice is that vulnerability, it's a little bit higher, or the distribution is a little bit larger on the conventional continuous flood, right? And in average, the vulnerability is lower in AWD and in SRI. In the case of the more extreme climate, the vulnerability levels are higher for the three systems, but it's still lower for AWD and SRI. Okay. Then when we look at the changes in mean net farm returns, you can see the difference between the orange, blue, and gray, right? So there is an increase in net returns in the less extreme case, in the less extreme climate. There are a few that have negative returns, but the percentage is small. The spread, again, on the conventional continuous flood is much larger compared to the AWD and SRI. But what is more interesting is looking at the more extreme case, where the losses are much higher on the continuous flood compared to AWD and SRI. The last row is an estimate of a change in poverty rates in the region. And this is associated, of course, to the income levels, in this case, the net farm returns. So when farm income increases, poverty rates decrease, right? So what this is showing is that under the conventional with AWD and SRI, poverty rates can decrease under the less extreme climate change. But poverty rates in most cases would increase under the more extreme climate change. But one thing that is important to mention is that even though we see these positive impacts or gains in terms of farm income in these cases, still the level of vulnerability in the region is quite high, right? It's between 40 and 50% or even more in the conventional continuous flood. So that's an important message, because you can have some gains in terms of the average in the population, but the level of vulnerability is still quite high, right? 40 to 50% of farmers that may lose because of climate change is high. Okay, let's move to the next results. This is the adoption, looking at the red ones you see in this table, this figure. The red ones are the results for switching from conventional continuous flood to conventional AWD. And the light green or light blue, depending how you see the screen, is switching from conventional continuous flood to SRI. The first row is the potential adoption rates. And you have the three climates, right? The current climate is the first column, and then the less extreme and the more extreme climates on the next columns. So switching from conventional continuous flood to AWD have a potential adoption rate of 50% under the three climates, right? So you can see the red ones in this row. But switching to SRI has in several of the regions much more or higher adoption rates that could go to close to 65, 68% in the current climate, and about 60 something in the less extreme, and it's very similar in the more extreme case. But what are the gains in terms of switching from conventional continuous flood to AWD or SRI? So the next row is again the proportion or the percentage change in farm net returns. So in both cases, either switching to AWD or SRI, you see the change in net returns is positive. So there are gains in both cases. So farmers would gain by switching from conventional continuous flood to AWD or SRI. But as you can see across this row, SRI provides the higher benefits, meaning farm net returns increase much more compared to just switching to AWD. And then the last row, as I said, it's connected to the levels of income. It shows that poverty rates decrease in both cases. So these two management systems, AWD and SRI, have the potential to reduce poverty in the region. And SRI seems to be the one that provides even larger benefits across the different climates. So that's when we look at those, let's say, economic outcomes in terms of climate change and adoption. But we are also interested in looking at the trade-offs in terms of, okay, so one goal is if we are interested in farmers' livelihoods, right? Increasing farm income and reducing poverty and all these livelihood outcomes. But also we are interested in reducing emissions, right? So the next slide was what we want to show is what are if there are co-benefits or trade-offs between these economic outcomes and environmental outcomes. So let's look first at what happens with climate change. And we're going to be looking at these situations, trade-offs, which can be win-lose or lose-win, meaning that in one indicator we can win, and then the other indicator we can lose, or the other way. Or if we have a win-win situation, which are the cost benefits that we win in the two indicators, or the worst case scenario, right? That we lose in both cases in these two indicators. So what we're comparing is one economic indicator, which is the change in mean net farm returns, versus 4 of the outputs from the NDC. The first one is methane, the second one is N2O, and then on the bottom is water use efficiency, and then the total emissions, the CO2 equivalent on the right part. And you can see the blue squares or the blue points is the conventional with AWD. The orange is the conventional continuous flat, and the green is the SRI. And then we have the two climates, right? The X is the less extreme, and the square is the more extreme climate. So looking at the first plot, the methane emissions compared to the net farm returns. One thing that we first notice is that the results with a more extreme climate increases methane emissions much more than the less extreme cases, right? And in terms of the systems, it varies. There are some larger conventional continuous flat, but there are also some larger AWD sites that have larger increases in methane emissions, right? But we also see that there are some farms or some sites that see an increase in farm net returns, right? Which is this top part. So this panel that I'm just highlighting, what it shows is that we have an increase in farm net returns, so it's a win situation, but we have an increase in methane emissions, so that's a lose situation. So that creates trade-offs between these two outcomes, right? We're winning with income, but we are losing with methane emissions in those sites. The bottom part, it's even worse because we're reducing farm income, and we are increasing emissions. So we are losing in those two dimensions, right? So that's a lose-lose situation. Now let's look at N2O. This panel that is in green, we are increasing farm returns, but we are also decreasing N2O emissions. So this is a win-win situation, right? So for these farms, when we're talking about farm income and N2O, we are achieving that situation, those co-benefits, this win-win situation. Then in the other quadrants, we have this win-lose and lose-win situation. So the upper one shows increase in farm returns, but we are increasing N2O. And then this bottom part, we are reducing farm income, right? But also reducing N2O. So there is a gain in terms of reducing emissions, but we are losing income. So for these few sites, it's also a lose-win situation. And then this is the one that we don't want to be, right? The lose-lose situation in those cases. So I'm just going to move faster on the other one. So same thing on the water use efficiency, we have a win-win situation where we increase farm income and also increase water use efficiency. And then we have some trade-offs and a little bit of lose-lose situation. And in terms of total emissions and CO2 equivalent, it's very similar to methane, right? So we have some trade-offs in many of the sites, but we also have some cases where we lose in the two dimensions. So that's the status in terms when we're talking about climate change. But now let's look at what is interesting to see, which is looking at the adoption case, right? So moving from conventional continuous flat to AWD and SRI. Again, the red dots are the case where we switch from conventional continuous flood to AWD, and the blue or light green is when we switch from conventional continuous flood to SRI. Same thing, look at the change in farm income and the change in methane emissions. So by switching those systems, in both cases, we reduce methane emissions, and in both cases, we increase farm net returns. So this is a win-win situation, right? Just by switching from conventional continuous flood to AWD or SRI, we are reducing methane emissions. In terms of income, SRI seems to provide much more increase in terms of income. And in terms of methane emissions, it's very similar, right? In the measure of change of methane emissions. Looking at N2O, it varies a lot. Yeah. So we have one case where this panel here on the left, where we reduce N2O for these cases and we increase farm net return. So that's a win-win situation. But there are trade-offs in other cases, right? And we can talk more about that or talk and say a little bit more about why we have this large distribution of results in terms of N2O, which has to do really with the heterogeneity and the amount of fertilizer that is being used on some of the sites. Then going on the bottom, the water use efficiency, the same thing. In most cases, we have a win-win situation. There are a few sites where water use efficiency is not improved, right? And then finally, on the C2 equivalent, we have, again, it's a reduction of emissions and an increase in farm net returns, which seem to be a win-win situation. And with some farms that have less reduction, but higher farm income. So that's the kind of analysis that we are able to do with this approach, looking at the benefits or the co-benefits and trade-offs in these different dimensions, right? In other studies, we also have, for example, indicators about food security or food insecurity that we can couple with this type of analysis. And it really talks about what is the goal, right, of policymakers. If the goal is increasing farm income, then maybe we don't care so much about emissions. But if our goal is also to reduce emissions, then we need to look at these trade-offs, right? And see what is important and see why some of these farms are not responding or behaving a different way. That's why this heterogeneity is important. Okay. So just quickly, I'm not going to in detail, but as a way to look at this analysis, as I said, we focus that on 3 districts, but we also had data for other districts, and let's think about this as a way to extrapolate this analysis to 6 other regions in Bangladesh. We look at the conventional continuous flood and AWD, and again, not going to go in detail, but if you are able to see the table, the first part is the climate change, the first table. And you see the variability that exists in terms of vulnerability, right? Between 26 to almost 50% vulnerability under the less extreme, a much higher vulnerability, even 95% in some cases under the more extreme climate. And then you also can see the changes in net returns and the different outcomes, emissions. And for conventional and then for AWD, the same thing, how the vulnerability behaves under the different climate change scenarios. And then the table on the bottom shows the adoption analysis under current climate and the 2 climate analysis for these regions, right? In some cases, adoption rates, for example, you have really low adoption rates under the more extreme climate, like 20%, going from conventional to AWD, and compared to the next one, which is 48%. So the question is, what is limiting these adoption rates in those cases, right? And this is a way to show that in some cases you can have higher adoption rates. It's possible, but in some others it's small. And then why is that? That's the question, right? Is it access to markets? It's biophysical conditions, and so that's part of a follow-up study that needs to be done. So just to finish, sorry, I think I'm over my time, I guess. Just to finish some conclusions of this analysis. So as I said before, a more extreme future climate reduces farmland returns and increases poverty rates in most sites, and also increase greenhouse gas emissions, right? There are a few sites that gain from climate change, but in most cases, there are losses in that more extreme future climate. However, in the less extreme future climate, we may have a small positive impact on farm income, right? And remember, the less extreme future climate, I think, if I recall correctly from what Sonali mentioned, it's not, it's driven more about temperature than precipitation, right? Then adoption of conventional AWD or SRI under the current future climate show strong reductions in greenhouse gas emissions, like methane and the total CO2 equivalent. N2O on the other side vary across sites and farm types, small versus large. As I said, probably because of the biophysical conditions and the inputs they use, like fertilizer quantities, organic fertilizer, and all of that. Water requirements for irrigation are reduced. And then, so both conventional AWD and SRI show potential co-benefits in reducing emissions and increasing income, right? So when we switch from conventional continuous flood to these two systems, and which can provide these desirable win-win outcomes. SRI show the largest benefits compared in these two systems. And when we look at those systems under climate change, or those changes under climate change, it looks like these two systems are more resilient to climate change compared to continuous flood systems. Then, so this is nice in terms of what was shown, but in practice, there are factors that limit the full benefits of these systems, right? For example, access and control to water, labor issues. There are some discussion about mechanization. So there are other factors that may affect adoption of these systems. And that's part of what would be interested in a follow-up study. So the results show that site-specific conditions are critical. Okay, and for that, we need tools and approaches to capture biophysical and socioeconomic heterogeneity to be able to address these uncertainties. But also, we need to have appropriate data and to model these complex systems. That's something that we run into, and that's common that we run into our studies, is having appropriate data to model these different systems. So I think there should be an effort to invest in data collection and data sharing to be able to do this kind of modeling. And finally, the co-benefits modeling approach that we presented in this webinar, this enables more efficient screening of the potential interventions and their interactions across multiple sites or regions, and can also characterize the implications for multiple dimensions of agricultural sustainability, right? In this case, socioeconomic and environmental dimensions. So with that, thank you very much. You are welcome to visit our website, and we also have what we call AgMIP Impact Explorer. Here's the website where we've been adding some of our previous work in terms of this modeling approach. Thank you. Hero?
Thank you, Roberto. Thanks. There are a couple questions for you. Eboko is asking about if there is any video on how to apply the NDC model for predicting greenhouse gases.
Okay.
He's asking about video, but he want to learn how to use.
Yeah, we do not have the video for the how to use DNDC, but we provide a training course regularly. So if you are really interested in that, you can go to participate the training course. This is one way. And other ways, we have the documentations on the website of the model, so you can also go to there to download it, to learn it. Yeah.
Thank you. The other question is, when you calculate net farm return, are you considering carbon credits given to the farmers for switching from conventional rice production?
Not in this analysis, but
Yeah.
what I was saying before, for example, right? If our analysis shows that the adoption rates are 20%, really low adoption, but we want to make sure we want to promote these different management so we can achieve these win-win situations, increase income, and also reduce greenhouse gases, then we can look at what tools we have to increase those adoption rates. So one way is carbon credits, right? The other way is payments for ecosystem services for reducing emissions, and that's something that we can do with our modeling approach too. And in fact, I think in our work in India, we might be doing some scenarios that consider those aspects.
Another question is, how are these results being used by policymaker or providing advice to farmer at the national scale?
Yeah, that's a very good question. As Sergey presented at the beginning of the introduction, one of our goals is to be able to use this information for decision making, right? And AgMIP has invested many years trying to figure it out how to work better with stakeholders. And one way that we established was we need to involve stakeholders, decision makers in our research process from the beginning, right? Is not the same that, when we do our research, have our results and go to the Ministry of Agriculture and present our results and say, here it is, than involving them from the beginning so they know what it's about and they basically buy into our results and approach, and this can be used to inform decision makers. In this specific case of Bangladesh, we had some roundtables with stakeholders, different ranges from farmers and different organizations and the government to inform of these results. Now, as we said from the beginning, this was kind of a pilot project looking at these issues, but there are much more complex issues regarding farming systems, rice farming systems, and these technologies that would deserve more supplementary analysis or study, I should say. But our approach that we use and our results that we use in other countries have been used in many countries to either make decisions, inform stakeholders, and also farmers. I'm just talking about, I don't know if Eric, Tao, or Sonali want to add more to this.
So what's the ratio of the adaptation? Do you have any estimates in between adaptation of alternative wetting and drying? Farmers
Adoption
are
or adoption? I'm just trying to understand the question.
adoption of the new practice.
In what we found in the region, in these regions, what currently is happening is a lot of farmers, of course, the conventional and continuous flood is the traditional rice system. But what we found in this region is that a lot of farmers are already using AWD in different magnitudes, right? And perhaps that's why in our analysis, what it shows is that the potential adoption rates is about 50%, right? The one way that you would interpret it is so farmers would decide 50% would decide I stay under my continuous flood, and 50% say I will switch to AWD. But the question is what is behind that? What is driving those adoption rates? What are the constraints, right? If we show that AWD provides higher income or higher economic benefits, then why we don't have higher adoption rates? So I think that's the one of the key questions that we need to ask ourselves. What is limiting this the different management that provides higher benefits?
Well, thank you all, I think, for your time and the informative presentation. We are happy to send you the video. If you have more questions, please contact our presenters and they will be happy to answer your questions.
Sure. Thank you, everybody.
Thank you.
Thank you.
Thank you. Thanks.
Bye.
Great job. Thank you.